This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Which is the area where it's a sonic throat, and there may or may not be a sonic throat in the actual flow field, but it's the great advantage of A star is that it's a reference area, and even if you don't reach sonic velocity anywhere, you still need to know A star. What would be the area if it were sonic? And so I've written down here that rho AU is rho star A, capital A star. That's the area of the throat, and that's the mass flux. And so you could divide that mass flux by rho naught A naught and multiply by rho naught A naught, and then you get some function of gamma times rho naught A naught A star. And from the relationships that I've done already, I did them last time, yeah, that A star over A is therefore rho naught, A over A star is therefore rho naught A naught over rho U times some function of gamma, and that function of gamma is it depends on the specific heats. It's coming from the energy equation that I wrote down for you. That H star plus a half A star squared is H naught, the stagnation total enthalpy. So that you have this expression for A over A star in terms of gamma and Mach number. And that's a very important equation, and it's an equation for a perfect gas. If you assume the fuel, if it's a solid rocket motor, if it burns as a perfect gas, and typically the temperatures are very high, so it does behave a bit like a perfect gas. And it has a gamma which is not the same as air, of course. And so you need to put that properly into account. And so A star is a reference area that may or may not exist in the flow, and it requires the sonic velocity. And I showed you that as for A over A star as a function of Mach number, then I showed you this particular plot where we went from 1 to 2 back to 1 again. That's an all subsonic flow. Whereas in the lower case there, the bottom case on the right, we went from 1 to 2 to 3. 3 was sonic, and then as the area expands, the density falls, the velocity increases, and the Mach number is greater than 1. So the density is falling so rapidly that even though the area is increasing, and the velocity ultimately reaches a maximum value, and I showed you what that was. All right, now the question is, what determines the flow? So this was an important figure. You could see that if it was all subsonic, like the top curve there, the pressure starts at the stagnation pressure, drops as you increase the velocity, as if it was an incompressible flow, and then as the area increases, the velocity goes down and the pressure rises. And then if you change that downstream pressure further, then you could still have subsonic flow, and then ultimately you'd have a critical point where the flow is just less than Mach 1 at the throat and it recovers as a subsonic flow, and that's the top curve, 2 there. But if you have a downstream pressure that's low enough, then you'll continue to accelerate the flow, and the pressure will fall and you'll be on the supersonic branch. So that's the same as this bottom curve there, 1, 2, 3, 4. So 3 is at the sonic throat and 4 is downstream. And so if you had a downstream pressure, if you opened it out and you had a downstream stagnation pressure outside, then that will determine what kind of flow you have. And you can easily see that we're going to have to put in shock waves to make sense out of all of this. But before I do that, I want to draw your attention to the real case, which is not a perfect gas. And so if you're the engineer and you're trying to work it out, what are you going to use if you can't use a perfect gas? And you're going to have to use an equation of state. And that'll have to be a canonical equation of state, like H as a function of S and P. Enthalpy is a function of the entropy and the pressure. And then we know that from the thermodynamic identity that the first law is dq is dE plus pdV. That's the first law of thermodynamics. And since H is E plus PV, then, if it's a reversible process, the dq is TdS, and TdS is therefore dH minus VdP, and that is the thermodynamic identity, and that is terribly important. You absolutely must know the thermodynamic identity. So now, what you can see immediately from that thermodynamic identity is that the specific volume, TdS, is dH minus VdP. So dH dP at constant entropy, the left-hand side is 0. dH dP is therefore equal to the specific volume V. And the specific volume V is 1 upon the density. So what is the speed of sound? A squared. And we're going to see later why it's called the speed of sound. We may even get there today. We said that by definition, A squared was dP d rho at fixed entropy. Well, if dP d rho would be dP dV dV d rho, right? And dV d rho would be minus 1 upon rho squared, which is V squared. So A squared is dP dV at constant entropy times minus V squared. Now, just to remind you here that if the density, and you can see that if you have H of S and P, then you have, you can also work out dH dP at fixed S. You can work out V of S and P, the specific volume of S and P. And therefore, dV is dV dP. V is a function of S and P. So it's dV dP at fixed S, dP, plus dV ds at fixed P ds. And an important point here is that if you divide that equation by dV and you make ds identically 0, then 1 is equal to dV dP at fixed S times dP dV at fixed S. That's quite important because we need to work out here what's the speed of sound squared. So it's minus V squared dP dV is the speed of sound. A squared is minus V squared dP dV at fixed S. So A squared is minus V squared by 1 upon dV dP. at fixed S. But V is dH dP at fixed S. So the minus V squared is minus dH dP at fixed S all squared divided by the second derivative of H with respect to P, d2H dP squared, because it's dV dP. So if you take, I don't have a pen here, but if I take so V is dH dP, so dV dP at fixed S is equal to d2H dP squared at fixed S. So that's how I got that expression, and that means that if I have H of S and P, it automatically means that if I have that as a function, I can automatically work out what A is as a function of S and P. And that's going to be very important. So if you are stuck as an engineer without a perfect gas, this is what you have to do. No ifs or buts. And since T, now let's just remind ourselves of that. T from the thermodynamic identity, T ds is dH minus P dV. So T is therefore dH ds at fixed volume. VdP, I'm sorry, I've written that wrongly. Yeah, I've written that wrong. That's VdP, dH ds at fixed P. Yes, that's T. Sorry. So if you had an arbitrary fluid and you were given T naught and P naught, and typically you might be, this is coming from the combustion of a solid rocket motor unit, you'll know what it burns at, what the fuel burns at, and you might be able to guess at what P naught will be, and then you can iterate that and find, because you know how much surface is burning and you've got some mass flux coming from the burning surface, and at steady state that's got to be the mass flux through the throat. So you can work it out. So since T is dH ds at fixed P, and therefore if I'm given T naught and P naught, or S naught and P naught, I can find H naught and A naught. And now H star at S naught and P star, so I'm working out what's going to happen at the throat. H star at S naught and P star plus a half A star squared is equal to H naught at S naught and P naught. So that's the fundamental equation. And now how would I solve it? Well, I'd choose, for example, a P1 star. And that, once I had a P1 star, if I knew P1 and I knew S naught, I have H1 star. And then I can, as I've just shown you, I can work out A1 star. And I then have to satisfy equation 1. And if I don't satisfy equation 1, then I've got to iterate on the pressure until I can find H star and A star. Yes?
Here between H star and H naught, we are assuming same entropy, is not? Is isentropic?
It is isentropic. You see S naught on both sides. It's the same entropy. And that's the equation that comes. That's an energy equation. It's not anything else. It's the energy equation for an arbitrary fluid.
But your H naught on the right-hand side is the stagnation entropy, right?
It's the stagnation enthalpy or the total enthalpy. It's the as if you were far, far upstream where the fluid is at rest.
But the equation above only holds for constant P, right?
No. Which one only holds it?
T equal dH over ds constant P.
Oh, T is dH ds at constant pressure. So if you're given H as a function of S and P, I can hold the P fixed and find the change of H with respect to S if I'm given that function. It's a partial derivative, and that's must be the temperature. Must be the temperature. Why? Because it's the thermodynamic identity. It came from here. dH minus VdP. So T is dH ds at fixed pressure, which is what I've written up there. So now, once I've iterated and found P star, which may or may not exist in the flow, there may or may not be a throat. You may not reach Mach 1. And when you initially ignite the solid rocket motor, you won't have reached Mach 1. It'll be subsonic flow. So you iterate on P star to find H star and A star, and you can also find, because you can find V star, you can also find rho star, because V star is dH/dP at the same entropy, and that's at the entropy of S naught, the original entropy. And then the mass flux through the throat, if you had a throat, would be rho star times A star times A star. So now, if I was given an A star, so I have a supersonic nozzle, and I know what that A star is, then what's the maximum mass flux that I can put through this nozzle? So, or I might be given the mass flux from the burning of the solid rocket motor, and I've got to choose the correct A star because I want to be at a sufficiently high pressure. So how do I work that out? I've got to find U, P, and the Mach number as a function of A over A star. So what I could do is I would first choose a P, and that necessarily means that I've got an H if I'm given H of S and P. It also means that I've got a specific volume and a density, which is dH/dP at fixed entropy. It also means that I can calculate the velocity at that pressure, because that's going to be the square root of 2 H naught minus H. And I know H naught, and I know H at that pressure, and so I know U. And I can work out my speed of sound, which is minus V squared, or dH/dP all squared, divided by d2h/dP squared, and that leads me to an A. So I can find, if I have rho AU, and that's going to be equal to rho star, A star, A star, that's the mass flux. So at P, I now know rho and I know U, and that leads then, in that equation there, for the mass flux, if I know the mass flux through the throat, then I know A, and I know A over A star, because I've already worked out rho star and A star from what I just did up above. So that means that that means I can find everything. I can find P, rho, U, and A, and the Mach number, that's U upon A, and H as a function of A over A star, given the equation of state. I must know an equation of state. Okay. Now, we've already hinted at shock waves. And I'm going to introduce shock waves not by talking to you about the method of characteristics and traffic flow, or although I could, I'm going to talk to you about shock waves in the context of compressible gas dynamics. And I said that I thought that it was likely that the only way we could satisfy the pressure relationship is if we put in a discontinuity. And the two problems that are going to motivate this discussion of shock waves are, firstly, this Laval nozzle, this nozzle where the pressure is, now let me just go back here. The pressure is independent, I don't have a pointer, but you can see from the top figure there that if I have a pressure somewhere between where those two arrows are, then I'm not going to match that pressure unless I can put something into the flow. Because on the subsonic branch, which is the 2 branch, I have a high stagnation pressure, and on the static pressure, and on the lower branch, I have a very low static pressure. So I can't satisfy the downstream pressure with a flow that I have to have some dissipation in the flow. This is for an isentropic flow. So I'd have to have some dissipation in the flow, and I'm going to think about is there a possible discontinuity for this flow? So I've done that, and I've done that. And now we're talking about discontinuities. And so here's my schematic of what could happen. I come down here on the supersonic branch. I go through a sonic throat. The pressure falls to 0.528 if gamma were 1.4. If the pressure, and then it keeps falling if I'm on the supersonic branch. And then if I had a discontinuity that took the flow from a supersonic flow to a subsonic flow, then I would recover on a subsonic branch, and you can see how I've drawn that going up as the area gets bigger, the pressure rises in a subsonic flow. And I could match P2 if I put in a discontinuity. So that's physically what is motivating what I'm about to do. But another problem that also motivates it is an Euler flow in front of a bluff body. So let's suppose we have a wing. So I've drawn a wing here, and it's in supersonic flight. So we have a supersonic flow moving. So if the wing is steady, we have a supersonic flow moving from the left to the right. Now, it's obvious that that flow, the streamline that I've drawn, and I can't point to it, but I've drawn these parallel streamlines coming in, and I've drawn this discontinuity because I know that the streamlines have to part to go around that body. And if the streamlines part, it means the area has got bigger. But if the area gets bigger and the flow remains supersonic, what would happen? What would happen? The velocity would increase, and it wouldn't stop. You wouldn't get stagnation right there at a stagnation point on that airfoil. So that's an impossibility. There must be some explanation for what could happen. And the only obvious explanation is that some discontinuity occurs, and I go from supersonic flow through the discontinuity to subsonic flow. And now, if I had a discontinuity that would take me to subsonic flow, then the area expanding and the velocity would go down. And I could have zero velocity right at the stagnation point. Is that obvious? Is there anybody? For God's sake, I get so nervous that you don't ask questions. I can't believe it. You're too afraid. I don't care. You're here to learn. You will never learn if you don't explain what you don't understand. You won't. You're wasting your time. So you must explain what you don't understand.
Hey Gary, I've got something I don't understand. When the rockets are actually built in practice, right, the pressure varies as you go throughout the atmosphere.
Yes.
And the rocket is leaving Earth.
Yes.
So, but everything you've described rests on the pressure differential. So how as a designer do you say, oh, but the pressure's going to change at the exit?
Right. So initially, you're going to put a shock wave in that nozzle. And that could be very dangerous, and that's what happened in the Titan IV solid rocket motor unit. You put a shock wave in that nozzle, and in order to compensate, because the thrust was now no longer axial, they moved the rocket nozzle to compensate for the thrust not being axial, and they ran out of control. And it was very dangerous, very dangerous. However, what happens as you go to higher and higher altitude? The pressure falls, and ultimately you've got vacuum, and the pressure is more than low enough. So you've got flow, a full flow in the nozzle, and then you're going to have an expansion fan around the nozzle to drop the pressure even further. So why don't they make the nozzle much, much larger in diameter to get the maximum thrust? Well, you think about it. Yes?
Here, when you said the area would decrease after the shock, which area you mean? You mean the area in the front of the airfoil or?
The area of the stream tube. So I've taken two lines there, and they're a stream tube. The flow is moving horizontally. But now it's got to go around the airfoil. So if I made this a very tiny tube, I'm still going to have to increase the area. If I increase the area, if the flow was one-dimensional gas dynamics, the velocity would go up. That's incompatible with the velocity going to zero at the stagnation point. There must be a stagnation point where the fluid is brought to rest. Right? Okay. So now, that's the motivation for supposing a spontaneous jump in U, P, and rho occurs over a very short length. Is there a solution for the integrals of the motion? That is, we cannot use, and you tell me why, we cannot use the differential equations. Why? Beg your pardon?
It's not in continuity.
No. We can't use the differential equations because we don't know how thick that shock is, and we don't know the stresses in the shock. We couldn't work out what the heat fluxes are. And there may well be heat fluxes because the temperature will be higher downstream than it is upstream. So there are heat fluxes, there are viscous stresses, and they are occurring over a very, very thin length. In fact, the continuum equations may not even apply. The shock may be so thin, typically it's only about 3 mean free paths, 3 or 4 mean free paths. We cannot use the differential equations unless the details of the flow over a very short length, for example, the form of the stresses, is known. But that is not required for the integral relations. Why not? Why not? Come on, for God's sake. Why not?
Because we could apply the integral different.
Because the integrals, the conservation laws, are rates of change of something inside the volume, but if it's a steady flow, there's nothing changing inside the volume, plus the net flux out. So that's only what crosses the boundary. I don't need the differential equation inside. Do you understand that? Is there anybody here who doesn't? Raise your hand, for God's sake. You don't understand it? Okay, I'll say it again. The conservation laws are of the form, the rate of change of something in the volume plus the net flux out of the volume is equal to a right-hand side, typically 0. In the case of mass, it's 0. So, if it's steady flow inside the volume, there's no rate of change of anything with time. Right? So all I care about is the net flux across the boundaries. So I don't care about the fact that there's a shock wave, perhaps, inside, where I can't work out the details. I don't need the differential equation. I don't need to solve the differential equation over a very short length, because I can't. But I can solve the conservation laws. That's a tremendously powerful idea. And you absolutely, if you're going to solve any kind of real engineering problem, unless you know that, standing on your hands, you'll fail. Guaranteed. Guaranteed. You'll be sitting around a table and they'll point to you and they say, "What happened?" And you'll say, "I don't know." And you'll leave. Nobody will pay you to stay. They won't. It's costing them $50 million to figure out why, and they're not going to have anybody there who doesn't know, who can't contribute to why it failed. So, okay. Yes?
Why do we assume steady state across the shock?
We are going to assume steady state. Later, we'll assume the shock moves and the fluid doesn't. But for the case of the wing, I can easily make the wing stationary and have a Galilean transformation that moves everything to the right. So if the wing's in steady flight, not accelerating, then I can do this. I can do it. So we're going to do it. We're going to assume steady flow in the first simplest case, and then we're going to do the more elaborate case where the shock's moving. All right? Okay, so now let's press on. But this is not required for the integral relations, only quantities on the boundary of the region and on either side of the discontinuity if the discontinuity is steady or moves at constant velocity. Because if it moves at constant velocity, I can put a Galilean transformation and put a control volume around something in which the discontinuity doesn't move at all. And I have steady flow. Right? So now, we're going to suppose that discontinuity is normal to the velocity, and we're going to work out jump conditions. And you are going to work them out while I do it. So you have to be paying attention or you won't understand it. So here's 1 and 2. 1 is upstream, 2 is downstream, and the discontinuity is the vertical line. Right. What is a statement in words of conservation of mass? Good God, nobody here can tell me what is a statement of words for the conservation of mass? No, that can't be right.
Mass cannot be destroyed.
Okay, so what is it in control volume terms?
Change of mass inside control.
The rate of change of mass in the control volume plus the net flux out equals 0. For God's sake. Right? You must know that. So There's no area change here. We're assuming a discontinuity, so I'm drawing streamlines that are parallel. So it says, so there's no change in area. So it says that the rate of change, there's no rate of change of mass inside the volume because the shock wave's not, the discontinuity is not moving. The flux out is rho 2 U2, and the flux in, the flux out on the surface 1 is minus rho 1 U1. Why? You got it right. Why? Because the normal's to the left, and it's U dot N, and U dot N is minus 1. So it's minus rho 1 U1 plus rho 2 U2 is equal 0. Consequently, rho 1 U1 is equal to rho 2 U2. Obvious enough, right? Or in terms of Landau and Lifshitz, he's written it as a jump in rho U, and the jump in rho U is rho 1 U1 minus rho 2 U2, and it's 0. Now we're going to do momentum. And what is the statement for conservation of momentum?
Rate of change inside the control volume, momentum inside the control volume plus the momentum cos the flux, cos the volume is the sigma force.
It's the net force in the ith direction. Rate of change of momentum in the ith direction plus the net flux of momentum out in the ith direction is equal to the net force in the ith direction. Okay, so what's the net force in the ith direction in this particular case? The net force in the positive x direction is what? Come on, for God's sake. What is it?
Partial difference.
You said the pressure difference.
What is the net force on the control volume? So here's my control volume. What's the net force acting? Huh? Pressure. Which way does it act? For God's sake. Here's P1 and here's P2. This is 1 and this is 2. What's the net force in the x direction? It's P1 times A minus P2 times A will be the force in the x direction, right? On the control volume. That's all there is. It's not complicated. Now, so that's the left-hand side because we're going to say the area is 1. Now, what is the net flux of momentum out of the volume? Come on, for God's sake. If it's the last thing I do, it's to make you, I'm not here for you to just write down every damn thing I say. That's a waste of your time and my time. Unless you're thinking about this thing, you're never going to learn it. Once you've learned it, you'll never forget it. So you've got to, what's the net flux of momentum out? It's the, you don't know? The net flux of momentum in the ith direction would be the mass flux times the velocity. And the mass flux here is rho 2 U2 times the area times the velocity. So it's rho 2 U2 squared. What is the momentum flux out on this surface? And if you don't get the sign right, you flunk. It's what? Speak up. minus rho 1 u1, and it's minus rho 1 u1 squared, right? Because it's the mass flux times the velocity in the x direction. So the jump in, so you can see that if I take the P2 to the right-hand side and the minus rho 1 u1 squared to the left-hand side, the jump in P plus rho u squared is identically 0. Now we're going to do energy. And what is the equation for the conservation of energy?
Mass flux times energy at the phase.
Nearly. In general, what is it? And if you must know it in general. Rate of change of energy in the volume plus the net flux out is equal to, beg your pardon?
Energy gain or work done plus heat.
Yes, plus heat supplied minus the work done. And you absolutely need to know that if you're going to do anything with gas turbines or steam turbines or windmills or any other power source. You must know what the energy equation is. And why is the flux of energy out got enthalpy in it, and the rate of change of energy in the volume has the internal energy in it? Come on.
This is because we add the work on the control volume
From the pressure.
on the pressure.
Correct. And we've left out, what have we left out? What have we left out when we've written this equation down? Come on. You have to know. You have to know. You must be sitting here like blotting paper and not thinking while I'm talking. And you'll flunk. You must think while I'm talking. If you're not learning while I'm talking, you flunk. So you have to think about it. What have I left out?
Heat,
Beg your pardon?
heat, Q,
I've left out Q. What else have I left out? Beg your pardon?
Work done is what you said.
Work done by the viscous stresses. I've left out all of the potential work that might have been done by viscous stresses. Why can I leave out the work done by the viscous stresses in the discontinuity? Partially, probably because it's zero. The discontinuity is stationary. So the work done is zero. Tau times U is zero. So we've got to work out the net flux of energy out of the volume. So we need a mass flux and the energy transported per unit mass. How much energy is transported per unit mass? Come on. How much kinetic energy is transported per unit mass? A half U squared, right. How much energy is transported per unit mass by the internal energy? E. Great. And so the H came from the pressure work done. And that's how we got H into the flux of energy out. We included it in the pressure work done. So we've got H plus a half U squared. And now, what is the mass flux? It'll be rho u per unit area. So it'll be rho 2 u2. And what is it on the other face?
Minus rho 1 u1.
Correct. Well done. So the energy equation is simply the third line that I've written there, rho 2 u2 h2 plus a half u squared minus rho 1 h1 plus a half u1 squared. And that's equal to 0 because I've left out any heat supplied to the volume and I've left out viscous stresses. So I've kept the enthalpy. And so I've got the change in enthalpy, the jump in enthalpy, h plus a half u squared is 0. So what's the jump in total enthalpy? 0. Correct. The jump in total enthalpy, HT is h plus a half u squared. It's the total enthalpy. It's the enthalpy if you bring the fluid to rest. So the jump in the total enthalpy is 0. And then, since we have, if we're given rho 1 and u1 and p1 and h1, then our unknowns are rho 2, u2, p2, and h2. 4 unknowns. I better have 4 equations. But I've only got 3. What's the 4th equation?
Perfect gas law if I have.
If I had a perfect gas, otherwise I have to have a canonical equation of state, H of S and P. And if I have H and S and P, then I have the specific volume, or 1 upon the density, which is dH dP at fixed entropy. And so from that I can get H as a function of P and rho. So I can solve for those 4 equations with 4 unknowns. All right. Now, let's recast this a bit. And for those of you who want to look it up, you'll see it described well, I think, in Landau and Lifshitz in sections 81 through 85. So the P2 minus P1 will be rho 1 U1 squared minus rho 2 U2 squared, which is rho 1 U1 squared into 1 minus, and since rho 1 U1 is equal to rho 2 U2, it's 1 minus U2 over U1, which is rho 1 U1 squared into 1, oh sorry, yeah, that should be rho 1 squared, is what I meant to write there. And U2 over U1 is rho 1 over rho 2, and I've pulled a rho 1 out in front, and I've got rho 1 squared U1 squared by 1 upon rho 1 minus 1 upon rho 2. And if I call rho 1 U1 an m dot, a mass flux per unit area, then it's the mass flux squared by V1 minus V2, where V1 is 1 upon rho 1 and V2 is 1 upon rho 2. And I know that H2 minus H1 is a half U1 squared into 1 minus U2 squared over U1 squared. And U2 squared over U1 squared will be rho 1 squared over rho 2 squared. And if I pull the rho 1 squared out in front, I'll have rho 1 squared U1 squared, which is a half m dot squared, and then I'll have 1 upon rho 1 squared minus 1 upon rho 2 squared. And so H2 minus H1 is a half m dot squared V1 squared minus V2 squared. Now, isn't that simple? Isn't that remarkable? And so if I divide one by the other, I'm going to cancel the m dot. Yes? Which one in the first equation there?
First equation,
I
And is the conservation of momentum okay?
yes, this is rho 1 u1 squared into 1 minus u2 over u1.
Well, what else do you think might be squared? Or is the row squared? No.
Yes, it's supposed to be. That's supposed to be rho 1 squared. And then this u2 over u1 is rho 1 over rho 2 from the conservation of mass.
So it's row 1, u1 whole squared.
Yes. So this should be rho 1 squared u1 squared, or m dot squared. And this one, when I put the u2 over u1 is rho 1 over rho 2, because rho 1 u1 is equal to rho 2 u2. So this u2 squared over u1 squared is, so you can see that this is a h2 minus h1 is 1 half u1 squared minus a half u2 squared, which is what I wrote down before. So I've written it this way. I pulled the half u1 squared out, and I put 1 minus u2 squared over u1 squared. And then I multiplied this by rho 1 squared because I have a, this u2 squared over u1 squared is rho 2 squared over rho 1 squared over rho 2 squared. And if I pull the rho 1 squared out in front, this will be a 1 upon rho 2 squared, and this will be a 1 upon rho 1 squared, because that will be the rho 1 that cancels, because I have to have a 1 there. So I can write it as a half m dot squared 1 upon rho 1 squared minus 1 upon rho 2 squared, which is a half m dot squared v1 squared minus v2 squared, where they're the specific volumes. The specific volume is 1 upon the density. It's the volume of unit mass. Right. So now if I divide these two equations, one by the other, I have h2 minus h1 over p2 minus p1 is, and you can see that a half m dot squared v1 squared minus v2 squared becomes v1 minus v2 into v1 plus v2. And the v1 minus v2 is going to cancel when I divide one equation by the other. And so I'm left with h2 minus h1 over p2 minus p1 is a half v1 plus v2. And I haven't solved anything. All I've done is use the equations that I have and rewrite them. And that is a very remarkable equation. It's called the Schoch-Hugonio. I don't know anything yet about H2, and I don't know. I just know that if I have a discontinuity, my conservation laws require me to have this relationship. So, in general, I don't know what the two conditions are. So I can say H minus H1 divided by P minus P1 is a half V plus V1. And that is the equation of motion for an arbitrary shock. I don't yet know how strong it is. We're going to talk about that in a minute.
Okay, we've got to wrap it up. Right?
Oh, good God. Okay. Well, let me just say one more thing here, and then I'll wrap it up. The equation of state is H is a function of S and P, and because you can use that to find the specific volume, that gives you H is a function of P and V. So I can rewrite equations 1 and 2 is the pressure is a function of the specific volume and P1 and V1, and that is called the shock Hugoniot. And it's